Now, I am going to just go through also two very important final steps that are in the textbook, but which I find, and this is important for the semester test, people have missed. So you'll see that there's this whole procedure in the textbook. The procedure in the textbook goes something like, define the deviation variables, substitute in the deviation variables, take the consequential products, so if there are something like derivatives, apply the derivative and take the derivative of the constant and have that become 0. And keep going until now you just have things in terms of the deviation variables. Then you can linearize that thing that we've already substituted the deviation variables into, and then you subtract the steady state equations. And then you find, as if by complete magic, that the steady state equations work out to be 0, right? Now, what people miss is that that is not really the procedure that I expect you to do. The procedure that I expect you to do is right at the end of that section, which basically boils down to this. If I have a derivative term of this kind, I know something incredibly important about this equation. If it is a derivative equation, what happens to those derivatives at steady state, by definition? Okay, so I know the derivatives will work out 0. So what does this mean? If I substitute x bar into this, I know the left-hand side is going to be 0. Okay, does that make sense? What that means is I can skip the step where I do the substitution and then substitute in the steady state and then do the subtraction and then, wow, that's amazing. Every time I do this, I end up with something that looks exactly like that. Right? Every single time, as if by magic, that C constant works out as 0. How can that possibly be? Because it's steady state. Okay? This is not something that's hidden. This is literally in the book. Right at the end, it says, okay, most of the time we can skip those steps. Most of the time, all that we need to do to linearize an equation and like in one step go from the original equation to a version of that equation which is linearized and in deviation variable form. The textbook has this formula in there that says we simply do f x, y, z is equal to, and then it has this equation, right? It says basically you take the partial derivative with respect to x and you evaluate it at the steady state. Okay? And that is the coefficient of x. Now that's an approximation, right? And then you take the partial derivative with respect to y and you evaluate that at the steady state and you multiply that, and that is the coefficient of y. And then you take the partial derivative with respect to z, you evaluate the steady state, and that's the coefficient of z. Now the application of that for this example that I've got here, because this is one of those, right? It's a derivative equation. We know the steady state version of that equation is going to work out to be 0. We know, and this is like reading ahead a couple of steps, but you must have come across this. When we do the linearization with Laplace, or sorry, with the linearization with the Taylor series, all of those Taylor series terms are like a coefficient times x minus the point of linearization. Right? That's kind of the form, plus c, right? But every one of those terms automatically includes like a deviation variable term already there. And so we can kind of fast forward and say, oh yes, well, I know that's every time going to happen. Every time. Like I don't have to think about it. It's just a mathematical truth. We go through the thing with the training wheels. Remember I told you there's a training wheels chapter. Chapter 3 is the training wheels chapter. It's a fiction. Like I never expect you, when I say substitute deviation variables and linearize, I'm not picturing you substituting deviation variables and linearizing. Right? I'm picturing you skipping towards the end of the chapter and applying this formula. Now, how does that work out? I look at that term and I say, okay, there's two variables here. They happen to be called x1 and x2 in this, but if I follow the exact same pattern, all I'm doing is I'm looking at that term and saying, okay, that term is only a function of x1, it could have been a function of x2. Let's be adventurous, right? Let's say, let's add a x2 so that the example is a little bit more nice, okay? So what does that term, how does that linearize according to the quick formula? According to the quick formula, that term will linearize as some a plus x1, or a times x1, plus some b times x2. Right? We know that that's what that's going to like work out as in deviation variables. Does everybody follow me? Because that's what always happens. Every time we linearize, we'll take a term and we'll rewrite that term to be some constant times the first variable plus some other constant times the second variable. And then this one, now again, most of this you're doing mentally, right? Because like, who has time to write these things down? It's perfectly fine if you kind of at least tell me what you're doing. You're saying, I'm linearizing. It's cool if you write down this formula. It's also cool if you write down this kind of formula for me. That's personally how I keep my thoughts together. But you now see that there's going to be a c times x2 term coming out of that term there, which also kind of tells you that the coefficient of x2 is actually going to be b plus c. Okay, but that's a whole different story. So we can skip ahead now, and what we're going to do is apply this formula. The first variable, which is x1, and you know, I'll skip ahead, but basically at the steady state here, we know that x1 and x2 are at the steady state are x1 bar and x2 bar by definition. And so who can quickly calculate what's the derivative of sine of x? It's cos of x, right? So we're going to have cos of x1. So that a coefficient is going to be cos x1 bar times x2 bar. Does that make sense to everybody? So I take the partial derivative dx1. I substitute in that partial derivative the values at the steady state, which are just the barred versions. And that's my coefficient. The important thing to realize is that that is a constant. So in other words, that bit there, right, that's a. Yes?
So if we would have replaced x2 with x1, would it have been cos bar x1 bar x1 times the change of x1?
I'm sorry. So if you're saying if x1 and x2 were...
Like x2 was an x1, sorry? Like, would you have also then gotten a...
Oh yes, I understand. If you had a more complicated expression, you would obviously do the full derivative, right? Like, so it would be still now the product rule or whatever. You know, my advice is most of us can do simple derivatives very easily. You know, so by now you've probably memorized like the full list of trigonometric derivatives, and like you know how to do the derivatives of powers and so on. And if you're like an overachiever, you know like what the derivative of log is or whatever, right? But most of us don't really have the patience to work through the full quotient rule, right? And so for me, if I see a quotient, I just pull open SymPy. But if I see simple derivatives like this, it's going to be a lot faster. Just think about the time that it takes to define a variable in SymPy and then go through, you know, like you save yourself a lot of time if you just mentally can do that derivative, okay? So now we've got b, okay? b is the partial derivative of that term with respect to x2, right? And how do I know it's with respect to x2? Because that's the one that that's the thing that I'm targeting over there. So I do the derivative with respect to x2. And so now I've got, again, sine of x1 bar. Why? Because that's just the thing at steady state. And that is the coefficient. Remember, the x2, the partial derivative of this term, I've noticed actually it's terrible when I do the YouTube videos and I actually use my finger during lectures, because then there's this whole piece of like, oh, and we can see over here, but nobody can see. So let me try. So we can see over here that if I take the partial derivative of that, right, it's only that actually this system is, given that x1 is constant, which is kind of what the partial derivative asks us to think about, right? It's a linear term in terms of x2. Is that making sense? So if we look at it from the x2's point of view, so I could actually have skipped that part. I didn't have to do the partial derivative. I could have just said, well, that's already linear in terms of x2. We reach the same conclusion, right? The derivative in terms of x2 is just sine of x1. The partial derivative in terms of x2 is just the sine of x1. But that leads to x1, x2 prime, plus, and now we just have to do this term, which is really simple. That's the derivative is 2x2. At steady state, that's 2x2 bar. Right? Quick, easy, no like substitution, no manipulation. It will always, always, always work this way for equations that have a derivative on the left-hand side. Does that make sense? So the second trick is that this works as long as we use the residual form for equations. It still works for equations that don't have derivatives on the other side. Right? Think about it. At steady state, those equations must be true. And so when we substitute that equation into, so now for instance with this equation here, p is equal to x1 whatever, right? If I subtract p from that, that is always going to be equal to 0. And according to very much the same reasoning, I can again do the same thing and discard those constant terms. And so by the time we're finished, every single one of our equations, some derivative equal to a linear combination of the inputs, or some equation which boils down to a linear combination of the inputs. There will never be a constant left, ever, after we've done our deviation variables and written and linearized. And so we can use this knowledge as a fast forward on the tedious plugging in and working through of those equations. So don't take my word for it. Go and look in the textbook, right? Just read ahead on the textbook and you'll see those two kind of summary statements which say for normal algebraic equations, this always works because of the equality, and for differential equations, this always works because steady state. And then you never ever in your life have to think about the actual substitution again. We do it at the beginning just to get a feeling for how it works. After you've done like 2 of them, you realize this is like magic. Every time I substitute steady state and I subtract it, like that constant term goes away. But it shouldn't have surprised you that much when you looked at the math, right? It's the reason why we use deviation variables in the first place, is so that those constant terms can fall away. So, are there any questions about this procedure? So I just want to make this incredibly clear. I'm going to edit this out so that there's one little piece that says like, this is how you linearize and write in terms of deviation variables, okay? This is what I'm expecting you to do. You're not getting pretty much any marks for the whole substitution method. I'm expecting you to jump immediately from the equation, like in the next line, and basically write down the linearized version. You're going to see me do it a couple of times in videos or in class, and you shouldn't be surprised when that happens. Now, the last thing I want to say about this, like as a high level concept, is this form, this idea that every time we do this, we end up with constant coefficient times x1 plus constant coefficient times x2. Now remember actually the constant coefficient of x2 here is b plus c, right? This always happens, and I've kind of forced you to do this in one of the tuts where I then ask you to write this in matrix form. Being able to write these equations in matrix form is a good check that you have in fact succeeded in making a linear version of it. I am backing away a little bit, like I'm in love with high order kind of data structures, call it in terms of math, because I realized early that there's this thing called working memory, or cognitive load theory, which basically says that you have about 7 working memory slots in your mind. All of us, pretty much, right? And you can do a lot of tests to show this, but basically it boils down to the fact that you just don't have such a good memory in terms of working memory, things that you can keep track of while you're going. So I learned that if you use big symbols, so like a matrix allows you to think about all of those things all at the same time and manipulate those equations simultaneously without wasting any time on symbols for the smaller equations. So if you can write 5 equations in matrix form, now suddenly you like using 3 symbols to describe all of those equations simultaneously. Okay, it's the same reasoning behind why do we make functions in Python. Because it's easier to read a program that's like 5 lines calling functions that are well named. It's easier to reason about how that program works than to actually reason through 200 lines of Python code with lots of loops and so on. So that's my bias, but I am walking back on it. So I encourage you to explore, but it's not as much a part of the course as it used to be. So if you encounter like me ranting about the power of matrix code formats and so on, it's important to me, but it's not really for exam purposes. So it's cool if you bypass that. You will save yourself a lot of time if you kind of adopt that work, but it's not necessary. The other thing that I wanted to say about the whole linearization effort is that once we are in this form, I want you to start recognizing these linear terms really, really quickly, even when they're kind of disguised in nonlinear form. So work through a couple of examples if that's kind of the way that you attack building a muscle memory on these things. But every time you see a big nonlinear system, you should remind yourself that every time you've linearized one of those, you get a sum of linear terms where there's one coefficient for every one of those variables. Right, so that shape is super important. And I'm, in some cases, going to be relying on that idea without doing the explicit derivatives and so on. Right, so I'm going to be looking at that and saying, well, I don't care what the relationship is. Whatever that relationship is, after linearization, it's going to be expressed as the sum of, or like a weighted sum of the inputs.